Hello, physics class. It's our Monday edition, and I'm sorry I can't be with you today. I took the day off to be with my daughter who is in from out of state for a short time. So I will leave you with these instructions. Let's look at what we were doing on Friday. Today's the 29th. Happy Leap Day. Let's see. Here's an idea that we had. Let me zoom out here and get the whole picture. Here is an example of a situation where we were able to conclude that the conservation of momentum applies because there's this system, and the system includes a cannon and a ball exploding out of it. And we have determined that there are no net outside forces acting on this system, so the law of conservation of momentum applies. So we're not counting the friction because it's a wheel and it's minimal. So, did you notice that the momentum before, P before, equals P after? And that is the basic formula that will help us through these problems. So here we notice that before the event, when the ball goes out of the cannon, that the mass of the ball and the cannon are 1, and the velocity of the ball and the cannon are 1 because they are in the cannon and the ball. The ball's inside the cannon. So there's one term here, mass of the combined cannon and ball, velocity of the combined cannon and ball. But after the ball leaves the cannon, then we have two terms. We have the mass and velocity of just the cannon by itself now, and the velocity, mass velocity of the ball. So I just wanted you to remember how to set that up. We actually did one with numbers, and I think we were looking for the velocity of the cannon, which we called recoil. So that was good. But then we did a second one where we had two cars, thing 1 and thing 2, and they collide and they connect as one. And we wanted to know which way it traveled. And we did mass. This time the two are separate before the event occurs. So we have mass velocity, mass 1, velocity 1, plus mass 2, velocity 2. They're separate in the beginning. But at the end of this problem, they are 1, the mass of the two combined and the velocity of the two combined. And we were looking for this. And again, we had numbers. And just wanted to remind you how this works. Let me show you one new fresh example. Would you please add this one to your day notes? What was it, day 3 notes on the law of conservation of momentum? So we have here a hopper. And a hopper, you may not know, is not always just something that hops, a person that hops or an object that hops. A hopper is actually a object like this. See if I can get you a real hopper. There's a hopper. And a hopper actually carries grain or fuel or sand or anything like that, rocks. And when called upon, it will release the contents into a truck, train, car, even a ship. So, this is a hopper. Here's my rendition of a hopper. And whatever is coming out of this hopper is entering a truck. So our problem goes like this. Here's a truck, and its mass is 1.2 times 10 to the third kilograms. Velocity is 2.2 meters per second. So sketch this. If you need it to pause, you may have someone pause this video while you're getting down the details. And so here's the truck as it approaches the hopper. It's empty bed, and as it approaches, it the driver stops using the gas pedal and the brake, so it's coasting at some point. And it'll start coasting, and as it comes here, it's coming out at such a speed, and the truck is going at such a speed that it doesn't even have to stop. It will coast right through this whole process and be able to fill the back without stopping or speeding up. So the question is, find the velocity of the truck after the grain fills it. Alright, so write down that scenario, the question, the information given, and the picture. Alright, so now we're going to actually set this up. So is this like the velocity momentum equation before? Is it two objects and then one, or is it one object and then two? Alright, the correct answer to that is we are going to set up mass of the grain, velocity of the grain, plus mass of the truck, velocity of the truck. So in the beginning, the grain and the truck are separate. So that's why there's two terms here. We're talking about the grain and the truck. Then, after the event has occurred, the grain is in the truck. So we have the mass of the grain plus the truck and the velocity of the grain plus the truck. So we go from two terms to one. We believe that the conservation of momentum law applies because there's minimum friction and no forces outside of this system. It's coasting. Alright, so let's put in the numbers where they belong. Let you pause this and attempt it on your own. Alright, when you come back, here is how it should have been set up. 1.2 times 10 to the third under mass of the truck. So that should go over here. Mass of the grain wasn't given. I'll call it mass of the grain. But before this event, the mass of the grain is all in the hopper. So we are going to assume that the mass of the grain and the velocity, the mass of the grain we don't know, and velocity of the grain is 0. Plus mass of the truck we do know is 1.2 times 10 to the third. Velocity of the truck we do know is 2.2, and that's going to be constant until the grain enters it. Then we have the mass of the truck plus the mass of the grain. I guess I do need to give you the mass of the grain, so we didn't really need it. When the grain is inside of here, before it has moved, we have the mass of the grain. If you would add this to your drawing, please. 7.4 times 10 squared kilograms. Sorry, we needed that, and I failed to give it to you. Alright, so this we know. We could have put that number in here. However, it's times 0, so it won't matter here. That's why I didn't really look for it too hard. So, come back to me. Okay. Alright, so now we have the combined mass of the grain plus the truck. So grain and truck. Those are added. So that takes care of this. And now I'm going to do velocity of the combined grain plus truck. Alright, so therefore I want to know what this is. So you may tap away on your calculators to find this answer. The velocity of the grain plus the truck. So after it enters, we find that it went way down to 1.4 meters per second. Alright, that is assuming there are no outside forces affecting this system. What if the velocity after loading the truck was known? So if you were driving this truck and you knew how much grain you were supposed to pick up, and you started coasting when you got near the hopper, and it filled the truck as you went under it and didn't stop, and you could see that your velocity went down to a certain amount. What if the velocity then after loading was known? Could you find the mass of the grain that went into the back of your truck if that was unknown? So this time the mass of the grain would be unknown. The velocity of the grain in the beginning is 0. It's just sitting in its little hopper. Then it falls into the truck, and then we would know the mass of the truck and the velocity of the truck in the beginning. Then we would know the mass of the truck, but we wouldn't know the mass of the grain. So that would have been another number in here. Right here, this would be the mass of the grain would have been unknown, mg. And then we would know the mass of the truck, and we would know this number. So suppose we knew this number, and we happen to be 1.4. Could you calculate the mass of the grain that went into your truck? So this would be the answer of course is yes, because we know everything except the mass of the grain right here. So this would be a good problem to know how to solve, because if you were promised a certain amount of grain, then you would be able to calculate how much actually went into your truck just by watching your speed after the grain entered your truck and solving this equation. So you could avoid rip-offs. All right. I just wanted to bring this back to mind so that you could remember what we did Friday and go to that pink worksheet where we were working on the back. And I don't think we started those. Brian, I think you accidentally did those. So I think you had a couple to correct or finish. So if you would, go ahead, and Miss Adams has the answers, so she will check them with you as you finish a couple. Have her look them over and see if you got the right answer. If not, go back to the drawing board and get those done correctly. When you finish, she has further instructions for you. All right. I hope you had a nice weekend, and I will be back with you tomorrow. So till then, over and out.